waveforms. So Dr. Anirban will initially provide his lecture on this topic, and at the end, in about 10 to 15 minutes, we'll discuss the questions. So feel free to ask the questions in the chat box, and we'll take up as many questions as possible at the end. Okay, so I think Dr. Anirban, you can start now.
Hello, good afternoon, everyone. Good afternoon, sir. So today's topic is the basics of mechanical ventilation. So I will not be bogging you with lots of information, and the agenda for today is catered towards the IDCCN trainees, the critical care junior residents and nurses, and CTCCM trainees. So it will be absolutely basic. We will not go into the advanced things and everything, and we will just try to have a beginner level discussion on mechanical ventilation. So yes, all good things start with a case scenario. A 35-year-old lady had fever, cough, followed by shortness of breath for 3 days, and she presented to your ICU where she got intubated because of severe acute hypoxemic respiratory failure. Now you are the nurse who has been assigned to this patient, and the patient is about to be put on ventilator after intubation. So as a critical care nursing staff, you should be aware of the operation of a mechanical ventilator and what are the initial ventilator settings that need to be put and how to monitor this patient on a ventilator. So today's discussion will empower you in some way in order to understand this basic prerequisites for effective ventilator therapy. So what is a ventilator? So when we think about a ventilator, and we have to choose a mode and set various parameters and different types of ventilators. All ventilators are different. So this really creates anxiety in the mind of people who are starting out. So in my presentation, I will try to make it very simple and let us understand what a ventilator is. So ventilator is nothing but it is a machine that uses some kind of power to do a particular type of work. So what kind of power? It can either be the power given by the gas pressures or the power or the electrical energy. So your ventilator can be driven completely by gas pressures when it is called pneumatic ventilators, or they can use electrical energy for its operations, or it can be a combination of both. So in majority of the case, it is a combination of both, where the gas pressures as well as the electrical energy is being used to do a particular type of work. So what is that work? The work is of breathing. So we, in our day-to-day life, we carry on doing our work of breathing. So it is so spontaneous that we go about doing everything and not thinking about the fact that we are breathing 24/7 throughout the day. When some sort of disease condition happens, we are somewhat incapable, or we need more energy to continue this work of breathing, and that is where the ventilator can come in extremely helpful in extremely sick patients in assisting the ventilation of such patients if they require external help to maintain adequate respiration. So complicated diagram, but I'll try to make it simple. So what does a ventilator do? The ventilator generates a flow across this airway. Can you see my pen highlighter?
Yes, it is visible.
Yes. So it generates a flow into the airway that ultimately goes and distend the lungs. So this is what ventilation is, right? Ventilation is a process where we expand our lung during inspiration by a flow through our airway. So in normal individuals like you and I, we do it by generating a negative pressure inside our thorax that drives in air from outside. In case of a ventilator, it is a positive pressure ventilation where the flow is generated by exerting a positive trans-respiratory pressure. Now, what is a trans-respiratory pressure? So trans-respiratory pressure is the pressure differential between the airway occlusion, the pressure at the opening of the mouth, or if you have an artificial airway, at the opening of that artificial airway, and the pressure in the body surface. Most of the time, it is the atmospheric pressure. So if you increase the pressure at your airway occlusion at the opening of your mouth or your or any artificial airway like endotracheal tube compared to your body surface, then you are going to generate a flow. Now, this trans-respiratory pressure can be divided into a trans-airway pressure and trans-thoracic pressure. So when the ventilator is ventilating a lung, it is generating a pressure to combat two types of forces which are impeding ventilation. So one is the resistive force. There is a resistance offered by any hollow structure if there is a gas flow across it, and there is an elastic force. So the lungs, if you consider lung parenchyma, individual alveoli together as a single compartment, it is an elastic compartment like a balloon. So whenever you inflate a balloon, you need some effort to overcome the elastic recoil of the balloon. So for that, you need to generate some pressure so that it overcomes the elastic recoil of the balloon and expands the balloon against its elastance. So we are dealing with two forces here, the resistive force and the elastic force. So the airway pressure, the differential that overcomes the resistive force is the transairway pressure, which is nothing but the pressure at the airway occlusion and the alveoli. So the airway occlusion pressure has to be more than the alveoli in order to have a pressure differential that generates this flow. And what is a transthoracic pressure? Transthoracic pressure is the pressure differential between the inside and the outside of the lungs. So the lungs will only expand if the inside of the lung has a pressure more than the outside of the lungs. So that is when it will expand. So in order to generate a flow, you need a positive trans-airway pressure. In order to expand the lung, you need a positive transthoracic pressure. Together, it is called trans-respiratory pressure. So yes, we know that the ventilator is a machine that does some work against some forces. So this is, if we draw the analogy, it is like somebody is pushing a cart. So while somebody is pushing a very heavy cart, he is doing some work to move the cart against the weight of the cart, right? So there is a force which prevents the cart to be moved from one place to another, and if you are moving the cart from one place to another, you are doing the work against that force. So you do work only against some force. So what is the, in mathematically speaking, what is the amount of work that they have done? They have if they have applied a force, say F, and to achieve a displacement, say D, then the work they have done is the product of the force they have applied and the movement they have achieved. So this is the equation of motion in a normal sense of things. What about ventilators? So in ventilators, in different scenarios, in our muscles or the ventilator or a combination, they generate a pressure, and this pressure drives a flow which eventually increases the volume of the lungs. So throughout this process, when the flow happens, it has to happen against some resistance. So this is the resistance provided given by our airway to the flow of the air. This resistance increases in disease conditions like COPD, bronchial asthma, or if you have too many secretions, or if you have kinking of your endotracheal tube, or partial occlusion of your endotracheal tube. Wherever there is a narrowing of this airway, the resistance increases, and therefore the pressure required to maintain the flow against increased resistance also increases. Now, for distending the lung, you have the ventilator works against the elastance of the lung. So, what is the elastance? Elastance is the property of any structure to recoil after deformation. So, if when you inflate a balloon, if you let the balloon, it will come back to its own original position. So, this is this nature, this physical property is elastance. So again, work is, in case of a ventilator, what is the work they have work a ventilator does, or say our own respiratory machinery does, is the product of pressure and volume. The pressure exerted and the volume of expansion of the lungs achieved. So this is the work done by a ventilator or muscle or both together. So in the simplistic sense of things, so far we have understood that the ventilator ventilates the lung by generating pressure, which initiates a flow, and this flow goes in and increases the volume of the lungs. Too much jargon here we have already described, so I'll skip this part. So coming to the equation of motion, that this is very important. So from if we have understood the previous cartoon, then we have realized that this is nothing but a mathematical representation of that cartoon. So the pressure of our muscles and the ventilator together. If we are paralyzed, sedated, no respiratory drive, then this will be zero. The ventilator will completely take over, and it will become a controlled mandatory ventilation. If, however, in majority of the cases, we also have some inspiratory efforts. So this is, in majority of the cases, a combination of the pressure generated by our muscles plus pressure generated by ventilator is equal to should equal the resistive and the elastic load that is impeding ventilation. So what is the resistive load? Like we have, this is offered by our airways against the flow. So this is the flow and the resistance of the airway. So this offers the resistive load, and the volume of breath and the elastance of the lungs, they offer elastic load. So when ventilator has to ventilate against this resistive load and this elastic load, and the pressure generated to overcome the resistive load is the trans airway pressure, which is nothing but the difference between the airway occlusion pressure and the pressure inside your alveoli. And the pressure required to expand the lung against the elastic load is the transthoracic pressure. So what is transthoracic pressure? It is nothing but the pressure differential between the inside and the outside of the thorax, right? Now we also we are more familiar with compliance, because compliance we measure in ventilators and all. So compliance is nothing but the reciprocal of elastance. So elastance is equal to 1 by compliance, or compliance is equal to 1 by elastance. So the equation of motion will therefore become flow into resistance plus volume divided by compliance. This is a very important equation of motion. This explains almost everything related to your ventilatory mechanics. So again, the equation of motion. So what does the ventilator do? So far we have understood that it generates a pressure in order to continue ventilation. So how does it generate a pressure? By influencing either of these. So this is the pressure, this is the flow, this is the volume. So the ventilator can control one of these variables. So this becomes the control variables. For example, the ventilator can be a pressure controller. So ventilator will say, or you through ventilator will say that I will ventilate this patient in a manner that throughout the inspiration, I will target a pressure that should be maintained. So this becomes a pressure controller. The ventilator becomes a pressure controller. If I use a flow controller, I will say that throughout the inspiratory phase, I will maintain a certain amount of this much amount of flow, say 50 liter per minute. I will maintain. It becomes a flow controller. And volume controller is that I will give this much amount of volume in throughout the inspiratory phase. So your ventilator can either be a pressure controller, or it can be a flow controller, or a volume controller. So when ventilator is a pressure controller, pressure becomes a independent variable. Pressure will be set by you, and the rest two variables will become independent. It will depend on the pressure that you have set plus the respiratory mechanics. What is the compliance of your lung? What is the resistance of your lungs? The other two variables will vary. Similarly, for a flow controller, this pressure will vary. And volume controller is actually, volume controller and flow controller are faces of the same coin, because in a volume controller also the ventilator eventually calculates that if I have to maintain this volume and this is the inspiratory time, so I'll have to maintain this flow. So when volume controller is eventually a flow controller. There is also something called time controller, which is advanced stuff. But however, if you are interested, time controller is when the ventilator cannot control any of these value, and it can just control the duration and frequency of your breaths. So that is seen in high frequency oscillatory ventilation. So yes. Okay, so here we can see that there are three types of breath, and this is the pressure, volume, and flow scalars. So what are scalars? Scalars are the tracing of the pressure, airway pressures, the tracing of the volume, and the tracing of the flow against time. Okay, so these are scalars. So other than scalars, what are the other ventilator waveform that we have? We have the loops. So we will come to that. So in this scalar, what we can see three types of breath: breath A, breath B, breath C. So breath A is what we can see that there is a square wave pattern in the pressure waveform, and the flow is a descending ramp pattern. We'll come to these flows. So we can see that throughout this inspiration, ventilator has maintained this pressure. Okay, and other values will change, can increase or decrease, flow can increase or decrease, volume can increase or decrease depending on the compliance of the lungs and the resistance of your airways. It will vary. So this is a pressure controlled breath. Okay. Next, coming to this, what we can see that in these two types of breaths, the ventilator has maintained the flow equal throughout the inspiratory phase, and the pressures can increase or decrease depending on the respiratory mechanics, and the volume can also, the volume will be maintained for the same inspiratory time, because volume is nothing but flow into time. So if the inspiratory time is say and the flow remains same, the volume will be same. So yes, B and C are pretty much the face of the same coin. Both of them are flow controlled breaths where pressure can go up and down if the resistance and the compliance change. This is a pressure controlled breath where the volume can go low or high. Flow can decrease or increase depending on the compliance and resistance of the lungs. This is a very important concept that we need to understand. So when we set a volume controlled breath, we know that we are going to achieve that volume no matter what the airway pressures become, unless the airway pressures become very high that it exceeds the alarm levels. So that is when the ventilator will not go beyond the alarm level for delivering the breath. So volume control breaths, you can assure the tidal volume as long as your airway pressures remain below the alarm limits, right? But in pressure controlled breaths, you can assure the airway pressure, but volume can decrease, volume can increase depending on the compliance and resistance of the lungs. For example, if you have a bronchos patient coming with acute severe asthma, severe bronchospasm, you have kept the patient on pressure control ventilation with a inspiratory pressure and a PEEP.
Dr. Dalim,
Yes. Hello. Yes, बोलिए.
Yes, ma'am.
Okay.
Okay, I'll
So
continue.
let's continue. Yeah.
So if in a pressure control ventilation, you have set the inspiratory pressure and the PEEP. Now the patient is in active bronchospasm, severe bronchospasm. He is generating only a tidal volume 200 ml. You have given bronchodilators, patient's bronchospasm is resolving. For the same set of inspiratory pressure and PEEP, the patient will be able to now generate 500 ml tidal volume. So the tidal volume varies in a pressure controlled breath. So why is this important? This is important because in a pressure controlled breath, we should always monitor our expired tidal volume, because there is a risk that we may be hyperinflating the lung if the lung is very much compliant, or there is a risk of hypoventilating the patient if, say, patient has suddenly the airway resistance has gone up or the compliance has gone down. There is a chance that tidal volume will come down, and without adjustment of the ventilator, patient may have severe hypoventilation. So this is why we should always monitor tidal volume in a pressure controlled breath. Now, what are the phase variables? So phase variables are nothing but the variables that that are set in order to define when the ventilator initiates a breath, when the ventilator cycles from inspiration to expiration. So these are phase variables. So we can see that a breath is divided here into the inspiration and expiration. The yellow regions are the expiratory regions, and the pink region is the inspiratory region. So something must tell the ventilator when ventilator should initiate inspiration. So this variable that tells the ventilator when it should initiate ventilation is the trigger variable. Okay. And something must tell the ventilator when it should stop inspiration and cycle into expiration. So this is the cycling variable. There is a variable that ventilator should target during the entire inspiratory phase. So this is either a pressure or a flow. So this is pretty much similar to the control variable, like pressure controller or flow controller. And there is a variable that it needs to target during the expiratory phase when it is not giving any breath. So usually it is the airway pressure during the expiratory phase, which is known as PEEP, which it maintains during the expiratory phase when there is no breath. Okay. So what are the phase variables? The trigger, the cycling variable, the target variable, and the baseline variable. So coming to trigger. So what are the two types of triggers? So when either you can tell the ventilator that I have set a respiratory rate of 12 per minute. So you should give a breath every 5 seconds, right? 60 divided by 12 is 5 seconds. So every 5 seconds, you give a breath. Do not listen to the patient. So that is called time triggered breath. Now, this is possible. This is done mainly when the patient is sedated, paralyzed, has very less of his own respiratory efforts, or patient is intraoperative or immediately post-operative. So that is when patient does not have his own trigger, and that is when the time triggered breaths are given, so that every 5 seconds a breath is given by the ventilator. If the patient has its own respiratory effort, most often they are kept on patient triggered. Okay. So how does a patient tell the ventilator that it should initiate a breath? So whenever you have a negative inspiratory pressure, negative inspiratory breath that you take, you generate a negative pressure plus a inward flow. So this little bit of flow that you generate, or the slight dip in pressure that you generate because of your inspiratory effort, spontaneous inspiratory effort, these cues are taken up by the ventilator in order to understand that you are trying to initiate a breath and accordingly give a inspiratory breath to you. So this is called patient trigger. So patient trigger can either be flow trigger, where your inspiratory efforts have generated a flow and this flow is picked up to initiate a breath, or it can be pressure triggered, where your inspiratory effort also leads to a dip in the pressure. So this is picked up and a breath is initiated. Now cycling variable. Cycling variable can be that you have set a certain amount of inspiratory time. So whenever we set a say volume control ventilation, we have tidal volume, P, FiO2, respiratory rate, and inspiratory expiratory ratio. So the respiratory rate and inspiratory expiratory ratios that we set are phase variables. They determine the phase variables. How? Cycling variable. The respiratory rate will determine at what time interval ventilator is triggered. For example, you have set a respiratory rate of 15 and a inspiratory expiratory ratio of 1:3. So what is the duration of a single inspiration and expiration? It will be 4, because 60 divided by 15 is 4. So 4 seconds will be the total respiratory cycle length. And you have set inspiratory expiratory ratio 1:3. So 1 second will be inspiration and 3 seconds will be expiration. So this is how ventilator calculates from respiratory rate and inspiratory expiratory ratio the inspiratory time. And at the end of 1 second of inspiration, it will cycle into expiration. So this is time cycled breath. If the patient is on volume control ventilation, sometimes it can be volume cycled also. Some of the advanced modes, they have volume cycled, where after a certain amount of volume is reached, it is cycled into expiration. However, volume cycling is in majority of the cases, it is like you set the tidal volume and the inspiratory expiratory ratio and respiratory rate. Accordingly, the ventilator will calculate the time of inspiration and the flow, because the volume divided by time is the flow. So it is majority of the time it is time cycle. Flow cycle is when the patient is going to tell the ventilator, okay, now you start expiration. So whenever a patient is on say pressure support mode of ventilation, so what happens is initially the patient has a high peak inspiratory flow, and then the flow decays. So this is the descending ramp flow. So you are able to set at what percentage when of initial peak inspiratory flow the ventilator should cycle to expiration. So this is flow cycle, and it is usually seen in the spontaneous modes of ventilations, right? What is pressure cycle? Pressure cycle is nothing but if your airway pressure is reached the pressure alarm settings. So suppose you have kept an alarm of 35 high pressure alarm settings. So the moment, for example, patient has developed bronchospasm. Initially, his airway pressures were maintained at 25. Now he has developed bronchospasm. You are not around, and now his airway pressure is reached 35. So the moment it will touch 35, no matter whether the entire volume of breath has been given or not, the ventilator will cycle into expiration. So this is seen only in the if the airway pressures have met the pressure alarm settings. So based on the timing, who controls the timing of the breaths? It can be a spontaneous or a mandatory breath. So a spontaneous breath by definition is the breath which is initiated and terminated by the patient. Patient's inspiratory effort has initiated and patient only will terminate the breath. So what is the trigger? The trigger should be patient trigger. What is the cycling? Cycling variable should be flow cycle. So only after, once the patient, once the inspiratory flow decays to a certain limit, certain level, the patient will cycle into expiration. The ventilator is cycling into expiration. So this is the spontaneous mode when the patient has control over the initiation and termination of the inspiration. So this is a spontaneous breath. If patient lacks control in the initiation and or termination, in either of them, if the patient does not have control, then it is a mandatory breath. So based on this, you may have three kinds of breath sequence. All the breaths are mandatory, so this is called continuous mandatory ventilation. All the breaths are spontaneous, so this is continuous spontaneous ventilation. Or there is a mixture. Some of the breaths are mandatory, some of the breaths are spontaneous breaths. So those are intermittent mandatory ventilations. Any questions so far? Like, can we take questions so far? Okay, so I'll move on. Complicated slide, just for the sake of inclusion, I have added. Forget the targeting scheme. This is advanced level stuff. We do not need to think about it. Just look at these two aspects. So ventilator mode, basically when we define ventilator mode, we need three parameters. One is the control mechanism, one is the breath sequence, and one is the targeting scheme. Control mechanism, we have already discussed that it can be either pressure control or a volume control. And breath sequence, we have already discussed, it can be a continuous mandatory ventilation, it can be intermittent mandatory ventilation, we have continuous spontaneous ventilation. Targeting scheme, I will skip. So we have two control variables, three breath sequence. Two control variables are volume control or pressure control, and breath sequences are continuous mandatory ventilation, intermittent mandatory ventilation, continuous support, spontaneous ventilation. Based on these two parameters, will create 5 basic modes. So it can be either a volume control continuous mandatory ventilation, volume control intermittent mandatory ventilation, pressure control continuous mandatory ventilation, pressure control intermittent mandatory ventilation, and pressure control continuous spontaneous ventilation. There is nothing called volume control continuous spontaneous ventilation. Why? Because how can ventilator control the volume when it has no control over the inspiratory time? It cannot control the volume. So it can only be pressure control continuous spontaneous ventilation. So these are the 5 basic modes that we have. You may have Hamilton ventilator, you may have Puritan Bennett, you may have GE ventilators, n number of ventilators. They will have different fancy names. Those are, but if you break them down into one of these 5 modes, you will understand what are the settings that you need to apply and what kind of mode it actually is. So this is the bare skeleton of what the basic modes are. The names can vary according to your ventilators. So it is a good exercise that whenever you have a ventilator you are not familiar with, you try to see the ventilator's settings and waveforms and try to classify amongst these modes. So this exercise will lead to greater understanding of the ventilator modes. Now, what are the usual settings in each of the modes? So this is a volume control ventilation. So initially, whenever you set this, the ventilator will ask for the tidal volume and the inspiratory time. So in some ventilators, instead of inspiratory time, the ventilator will ask for the respiratory rate and the inspiratory expiratory ratio. So these are basically the faces of the same coin. Also, PEEP and plateau. So what is plateau? We will come to that. So plateau is the inspiratory pause at the end of inspiration before the expiration starts. So how much percentage of inspiration you want to keep the patient at inspiratory pause? So that is the plateau. And this is the pattern of flow. So we will come to that. What are the different patterns of flow, and then we will revisit it again. So here we can see that there is no trigger variable that they have incorporated. That means this is a continuous mandatory ventilation, which will be time triggered. No patient triggered allowed. So this is useful only if the patient is sedated, paralyzed, and does not have his own respiratory triggers. Now, this is volume assist control. So in assist control mode, basically the patient gets to trigger the ventilator. The rest of the breath is ventilator driven mandatory breaths. Okay. So yes, again, tidal volume, inspiratory time, respiratory rate. This is what we have said. From respiratory rate and inspiratory time, you can find out the inspiratory expiratory ratio and PEEP. And here, see, the only addition is from the previous one is the flow trigger. So you have told the ventilator that if the patient generates a flow of 2 liters per minute, you give a breath. So this is a patient triggered breath that the ventilator will give, right? Now this is a pressure control, assist control. So instead of tidal volume, now we have the inspiratory pressure. So what is inspiratory pressure? This is the driving pressure. This is the pressure pressure that the ventilator will increase above PEEP and maintain throughout the inspiration. Okay. So if an inspiratory pressure of 15 has been kept and the PEEP is 7, so the you can see that PEEP is 7 here, and the inspiratory pressure control of 15 will be 7 plus 15. It will be somewhere around 22. So yes. So the ventilator will maintain 7 centimeter of water airway pressure during expiration, and during inspiration it will maintain 7 plus 15, 22 centimeter of water. Then again during expiration will come down to 7. So this is pressure control. Tidal volume in this case is a function of this differential this difference in pressure and the compliance and resistance of the lung. So those compliance and resistance of the lungs can change with evolving disease condition, and therefore tidal volume is subject to change. The rest of the parameters remain normal. Again, here they don't ask for the flow pattern, because the flow pattern in pressure controlled ventilation is always descending ramp flow. So pressure support. So what is pressure support? So pressure support is a continuous spontaneous ventilation where the patient will trigger the ventilator and patient will cycle the ventilator also. So instead of there is no inspiratory time. Yes, this is the maximum inspiratory time. If the patient does not cycle the ventilator, then at 2 seconds it will interrupt the inspiration. However, this does not come into play in regular scenario. So what comes into play is the expiratory trigger. So you have told the ventilator that once the flow, so the flow is descending ramp flow. So this is, say initial peak inspiratory flow was say 100. So once you come to 20 liter, once the flow decays to 20 liter per minute, 20% of the peak inspiratory flow, you cycle into expiration. So now the patient gets to influence the inspiratory time also by slowing the decay or hastening the decay of the flow. If the inspiratory time can increase or decrease, right? So now SIMV. So in SIMV, basically so it is a intermittent mandatory ventilation. What is S? Synchronized. So let us understand what intermittent mandatory ventilation is. Intermittent mandatory ventilation is where you will get mandatory breaths which are cycled by the ventilator with a specific inspiratory time, and there are spontaneous breaths in between, which is like a pressure support breath or a spontaneous. So now before SIMV mode did not have pressure support for the intermittent spontaneous breaths, but now it is always SIMV plus PS, SIMV plus pressure support. So the interim spontaneous breaths are also pressure supported breaths. So here we get a setting for the mandatory breaths, that is the tidal volume and the inspiratory time. This is for the mandatory breaths, and some settings for the pressure support breaths. So this is the pressure support and the expiratory trigger. So you get both settings that you see in mandatory assist control ventilation and pressure support ventilation together here, because this is a mixture of two modes. Once we go to the waveforms, it will be even more clearer.
Hi, Dr. Anirban. Just to update you that we have about 10 minutes left.
Sir?
We have about 10 minutes left.
Okay. I might need some more time, but I'll try to finish. So
yeah,
look at if we look at this waveform, we can see that the flow is a constant flow wave pattern. So the flow is controlled here. So if flow is controlled, what is controlled? The volume is controlled. So it must be a volume controlled breath, right? The pressure slowly increases as the lung inflates. So what kind of ventilation is this? All the breaths are mandatory breaths. So it's a volume control breath. It can be a volume assist control. It can be a VCV without assist. But basically the thing is that it is a volume control breath. So how do we understand that? So in a pressure control ventilation, you will see that pressure is constant throughout the inspiration. It will be a square. However, in a volume control ventilation, the pressure will slowly increase as the lung fills up. In volume control ventilation, the flow is maintained constant throughout the inspiratory phase. So it is a flow control ventilation. So nowadays, however, this has also changed. In today's ventilators, you can change the flow from a constant flow wave pattern to descending ramp flow pattern, even in a volume control ventilation. So the ventilator is advanced to that level. And this is the reason why, like I told you, that why this, what is this pattern? This pattern is that I have told the ventilator that you initiate a descending ramp flow pattern, unlike a square wave flow pattern that we usually see in volume control ventilation. So this is the advancement that has happened of late. So yes, what are the flow patterns? Two common flow patterns that we see is the rectangular flow patterns or the constant flow wave pattern, and this is the descending ramp. Spontaneous ventilation will have a sinusoidal flow pattern. Okay, so what kind of breath is this? Pressure control or volume control? So this is a pressure control, because you can see the pressure is targeted and maintained throughout the inspiratory phase. So this is a pressure controlled ventilation. Now, what are the information that we get from here? What kind of breath is this? This is a volume control, because you can see that the flow is square wave flow pattern. Also, you can see here that it is volume control. So no suspense there. what is most important here is this value. What is the peak airway pressure and the plateau pressures? So these are very high. The airway pressures are high. So now what does that mean? So coming to the most important aspect of your ventilator waveform analysis, we are going to discuss next. So SIMV, like we already said, that there will be mandatory breaths with interspersed spontaneous breaths. Okay, so we have to understand the concept of airway pressure. So far we have understood that your respiratory pressure is equal to the flow into resistance plus volume divided by compliance. So if what is respiratory pressure is the pressure differential between the airway occlusion and the body surface. So body surface area we consider it to be 0. So that then your respiratory pressure becomes airway occlusion pressure, or the pressure that your ventilator monitors. So when there is no breath being given, there is no flow. At that stage, the flow is 0, and therefore the resistive load component is 0. At that level, your airway pressure will be equal to the volume divided by compliance of lung. So if the volume should be above FRC, the volume above FRC. So if the patient is spontaneously breathing, you have not given any PEEP, so it will be 0. So 0 plus 0, airway occlusion pressure will be 0. But if you have given a PEEP, then the volume will be more than the FRC. So there will be some volume here and some airway occlusion pressure will be recorded. Usually it's a 5 centimeter, the PEEP that you have set. So now the inspiratory phase. So during the inspiratory phase, I have taken this as a volume control breath. So the flow is constantly maintained throughout and the pressure slowly increases. So what happens here? The flow is positive and it is constant. So there is a resistive component, constant resistive component is there. And the volume progressively increases. So this component progressively increases, and because of this progressively increasing elastic component, the airway occlusion pressure progressively increases here. Okay, initially there is a jump because suddenly the flow is initiated. This jump is because of the resistive component, and after that this progressive rise is because of progressive increase in elastic component because of progressively increasing lung volume. And we come to the end of the inspiration. After that, there will be no more increase. So this is the peak airway pressure. So what is peak airway pressure? Peak airway pressure is the flow into airway resistance plus volume by compliance. Okay. Now what happens is we give an inspiratory pause. So once we give an inspiratory pause, the flow again becomes 0. So till now we were having this, and suddenly this flow has become 0. So there is a decrease in the resistive load. So resistive load is suddenly not there anymore. So because of that, the pressure takes a dip. So pressure comes down, and this pressure is recorded as the plateau pressure. So what is plateau pressure? Since flow is 0 at that stage, plateau pressure is nothing but this component, elastic component, the volume inside the lung divided by the compliance. Okay, and the difference between peak and the plateau pressure is called trans airway pressure. Like if you remember trans airway and trans thoracic pressure, so trans airway is again, in another word, it is nothing but difference in the peak and the plateau pressure is the flow into resistance. So as the resistance increases, the trans airway pressure increases, the gap between the peak and the plateau pressure increases. And then the expiratory phase, what happens during expiratory phase? There is no pressure, it is a passive process. So the trans expiratory pressure is 0. So if this is 0, then this the flow into resistance becomes minus volume by compliance because their addition is 0. Okay, so this is very important. So in a normal individual, you can see that the peak and P plate are very closely placed because the resistance is not that huge. And This is a volume control breath. And this component of your pressure is because of the resistive load. And this component of your pressure is because of the elastic load. Okay. Now, what happens if, say, patient develops bronchospasm? The elastic load remains the same, and therefore the P plateau will remain the same. However, the resistive load will increase and the trans airway pressure will increase. Remember, trans airway pressure is proportional to the resistance. As resistance increases, the difference between peak and plateau pressure increases. So the peak and the plateau pressure difference increase, gap widens. It increases. Peak pressure increases, plateau pressure remains same because there has not been any change in the compliance of the lungs. However, if the compliance of the lung decreases, both plateau and peak pressure increases. So this is important, that peak pressure can increase both if the lung compliance decreases or the airway resistance increases. However, plateau pressure increases only if the lung compliance decreases. And by not just lung, the thoracic, entire respiratory system compliance decreases. So in which cases are we going to get this? In cases of bronchospasm, secretions, airways narrowed by kinking or any sort of mucus plugging. So this is when you are going to get a wide peak pressure increases, plateau pressure remains normal. In which cases both of these increases if the chest wall or if the respiratory system compliance has gone down. For example, ARDS, pneumonia, pulmonary edema, or say any pleural collection like pneumothorax and massive pleural effusion, or you have a very rigid chest wall because of chest wall edema or obesity. So this is where your respiratory system compliance goes down, and that is when both your peak and plateau pressure will be high. So monitoring this peak and plateau pressure will give us idea about your respiratory system compliance and your airway resistance. If you want to go deep into it, these are the calculations that can be done: the static compliance, airway resistance, and dynamic compliance. I will not discuss it in details here. So yes, again, the peak pressure and the plateau pressure both are high, and the gap is not so much increased. So this is predominantly a case of decreased compliance of the respiratory system. Okay, so this is how we tend to find out. Now, what happened to this patient? As you can see, the peak pressure alarm has been set off. The peak pressure is very high, and the tidal volume is not getting delivered. So this may be a case of partial or almost near occlusion of your endotracheal tube, and the patient is not getting ventilated. So this becomes an emergency. You should immediately put the patient on 100% oxygen and probably change the tube. What happened in this case? We can see that the inspired tidal volume is 870, however, the expired tidal volume is 214. So if you see the volume scalar, you can see the volume scalar abruptly goes down before meeting baseline. So this is a case of leak, extensive leak in the circuit. So from your scalars, you can also detect if the ventilator circuit has leaks. What happens if your flow waveform does not reach baseline before the next breath is initiated? So this happens when when your expiratory flow has not reached zero before the next breath is started. So this leads to a phenomenon called air trapping. So what is air trapping? The amount of air you have inspired, you are not being able to expire before starting the next inspiration. So this is seen in cases of our COPD patients who have reduced expiratory airflow, and for these patients, the phenomena of air trapping is very common. And as the air keeps on getting trapping, the end expiratory lung volume keeps on increasing. So this is called dynamic hyperinflation, and this is one of the most important reason for respiratory failure in our COPD patients. So yes, if the flow is not meeting baseline before the next breath is initiated, you should suspect air trapping and dynamic hyperinflation, especially in your COPD patients. Now coming to the pressure volume loops. So this, what is a pressure volume loop? You'll have a pressure in the x-axis and the volume in the y-axis. So this is a pressure volume loop of a spontaneously breathing patients. So what happens? Patient generates a negative pressure, and this leads to increase in the volume, and then at expiration it becomes a positive pressure because of elastic recoil of the lungs. So this is spontaneous breath. Now controlled and assisted breath. So in controlled breath, you can see this is the inspiratory limb and this is the expiratory limb. So this is the pressure volume loop. If you connect the two edges, the slope of this line gives you the idea of the dynamic compliance. So, what is an assisted breath? You can see a negative pressure trigger before the breath is initiated. So this is an assisted breath. So again, this is the airway pressure during inspiration. This is the airway pressure during expiration. This is the peak inspiratory pressure. This is the plateau pressure. And this is the trans airway pressure. Now, what happens with varying lung mechanics? So, as the compliance of the lung decreases, the curve is in a volume controlled ventilation, the loop is shifted towards right. The loop is shifted towards right. In a pressure controlled ventilation, the loop cannot get shifted towards right because the pressure is controlled. So pressure cannot increase. Rather, the volume will decrease. So it will be coming down. The loop will come down in case of a pressure controlled ventilation as the lung compliance decreases. So this loop can give us idea about the compliance of our lungs, right? What happens if the resistance increases? If the resistance increases, as we know, the trans airway pressure increases. So this will widen up. This will widen up. So we'll get a wide loop like this. This is a COPD patient with a wide pressure volume loop. And what else? This curve is shifted towards left. So it's a highly compliant lung. So in COPD, you get a highly compliant lung and the resistance is high. So this pressure volume loops gives us that idea regarding the respiratory mechanics. Also, we can use this pressure volume loop in setting our PEEP and our driving pressure during ventilating an ARDS patient. However, caution should be exercised that normal pressure volume loop that we see in our ventilator cannot be used to get this information accurately. This is done by using low flows, and something which I want to discuss here. So yes, in short, in the inspiratory limb, we have a lower inflection point where the alveoli are starting to open up, and the upper inflection point where the alveoli is beyond this are getting over distended. Okay. And there is a deflection point also in the expiratory limb. So deflection point is where the alveoli might start to get collapse. Okay. So the idea of ventilating the patient with information from this is that we need to ventilate in this area. This is the area with maximum lung compliance. So we should not go beyond upper inflection point. The PEEP should not go less than lower inflection point, or more importantly, nowadays they say we should use upper inflection point in the deflation limb in order to titrate PEEP. Your PEEP should be at least 2 centimeters more than this. Coming to flow volume loops. So what are flow volume loops? This is volume in the x-axis and the flow in the y-axis. So if you have a spontaneously breathing patient, you will see this upside down. But in a Controlled breath, positive pressure breath, the inspiratory part will be up and the expiratory will be down. So, so this is a normal flow volume loop. Now, what happens in comparison to a normal flow volume loop? What can we see here? So this is a COPD patient with air trapping. So you can see the flow has not reached baseline. So this is air trapping. And the peak expiratory flow has reduced. The flow expiratory limb is has been pushed up, and there is a scooping. So these are signs of increased airway resistance, and the scooping is a sign of increased airway resistance at the level of small airways. And there is a air trapping here. What can we see here? That the loop is terminated here before the volume has reached 0. So this indicates leak. The volume that has been inspired is not the same as that has been expired. So some of the volume has leaked. So this is flow volume loops. So far we have discussed the individual modes, the scalars, the airway pressures, and the loops, the basic level information I have given you. And I have kept this presentation, I've tried to keep this presentation very short in order to give time for discussion and question answers. Thank you.
Okay, so in case there are any questions, you can write in the chat box. First of all, thanks, Dr. Anirban, for the wonderful lecture.
Thank you.
You covered the topics in a brilliant way, and it's a difficult topic, and you have simplified it quite nicely. So, any questions from the audience? Currently, I don't see any questions. So, important points, I think, Dr. Anirban, if you just summarize for them the kind of take-home messages.
So the most important thing is that, when you set a ventilator, you should be you should be aware of what parameters to set and what needs to be monitored. So that is the most important thing that you should know. You can either choose a volume controlled ventilation or a pressure controlled ventilation. So in volume controlled ventilation, like I said, you have to monitor the airway pressures, because the changing airway pressures will give you an idea of the changing lung mechanics, whether patient has developed a new reason for decreasing lung compliance or increasing airway resistance. So these are the information that you will get in a volume control ventilation. In a pressure control ventilation, you have to monitor the tidal volume. That is, I cannot stress this more enough. I cannot stress this enough that you have to monitor the tidal volume. Your pressures are going to be maintained by the ventilator. So this is the basic thing about the ventilator modes. Rest, all of it is something that you have to go back and see in your ventilators, read, and build upon this preliminary knowledge from here.
Yes, very important point. And I would like to request all the students to, whenever you visit your ICUs, just keep a note of the ventilator mode, which mode the patient is in, and follow up that patient longitudinally over the period of days as the patient is improving, how the ventilator mode is being changed. Like from initial maybe control mode, volume control, or pressure control mode, patient may go into the pressure support modes, and then finally the spontaneous breathing trials and all. At the same time, have a note on how the different patients who are suffering from different diseases in your ICU at the same time are being ventilated. So this longitudinal and cross-sectional observations will help you a lot in understanding the clinical practical implications of whatever you have learned today. So that will be very important. So if there are no questions, I think we can call it a day. Excellent presentations again, Dr. Anirban. Thanks a lot.
Thank you. Thank you, sir.
Okay, thank you.